Hi everyone, in this video I'm looking at distribution shape of histograms. If you're new to histograms, I would recommend first watching the Interpreting a Histogram Basics video, which goes into the details about how to read a histogram and what we're looking at and how we use it to analyze numerical data. In that basics video, we left off with this example and talked about how we were looking at histograms to give us a sense of the center, spread, and any outliers in the histogram. Here we're going to shift over to talking about possible distribution shape types and modality. We sort distributions into a few general types, and I have some examples here that we can take a look at. Before I start looking at these specific graphs, I did want to let you know that I used Python and ChatGPT to generate these, so this is not real data. This is just to give you an idea of what types of shapes we might see in data and where those might arise. So the first graph we look at is the blue one on the upper left-hand corner here. The horizontal axis is labeled as height in centimeters, and we're imagining that these are heights for adult humans. The peak would be right around the middle, kind of the average height, and then they would taper off in both sides, and that's what we're seeing in the graph. So there's some very tall bars near the center of the height range, indicating high frequencies, and then the bars get shorter and shorter as we go off to the right and off to the left on the graph. This is a roughly normal distribution. It's symmetric on both sides. It has a peak in the middle. It kind of tapers off down towards zero frequency, roughly evenly on both sides of the graph. That symmetry is in contrast to what we would call a skewed distribution. So the graph to the right here, this is in pink. The title here says right skewed distribution. The horizontal axis is representing income in thousands. So annual income is typically a right skewed distribution. Again, this particular data set is not a real data set, but it gives us a sense of the shape. So most people have incomes on the lower end. In this case, on this graph, the highest frequency is down towards 0, and then we have lower frequencies going up to 20, and then towards the right-hand side of the graph, which goes all the way to 100, the frequencies get really, really, really tiny. We would call this a right tail, where the frequencies are kind of dropping off towards the right, and most of the data is grouped on the left-hand side of the graph. The higher frequencies are on the left-hand side. The skew terms can feel a little bit backwards, so we call this a right skew because there's a right tail. Even though the bulk of the data is on the left, this isn't left skew, this is a right skew. So income or things like housing prices and things like that tend to be right skewed because most values are more towards the lower end, and then we have a few people making much more money, or a few houses that cost a lot more than the typical that kind of create that right tail. In contrast, we have a left skewed distribution I have in this bottom left corner here. The example would be the age of retirement. Again, these particular data values probably are not realistic, but most people retire at maybe around 65, 70 on the higher end of ages, but then we have some people who retire much earlier. So if we're creating a left tail like we're seeing in this graph where the bars on the right are very tall, and then as we move to the left on the graph the bars get shorter and shorter, and then we just have maybe a few outliers much lower in the range with very short frequency heights on those bars. So that left tail indicates a left skew. All three of these examples, the normal distribution and the right and left skew, are examples of unimodal graphs, meaning they have just one general peak. On the right-hand side here, I have an example of a bimodal distribution where we have two peaks in the graph. So I have a peak, in this case the horizontal axis is labeled as test scores, and we have a peak around 60 and then another separate peak around 85 with kind of a dip in the bar heights in the middle. This one is quite exaggerated. Often when you see bimodal data, the peaks have a little bit less of a gap in between them, but it just depends on what data you're looking at. The reason bimodal distributions are important to consider is that they typically represent data from two separate populations that are being mixed together. So the example here was test scores from two different student groups. Maybe students, high school students took the same test, and one group took them in their freshman year and one group took them in their senior year. So the freshmen might have generally lower scores because they haven't learned the material yet, and then the seniors had higher scores. When we put them all into one graph, it creates two peaks within the graph. So if you did see this in data, it might indicate that you need to look closer at that population and split it into two groups if you could differentiate the two populations. The last distribution shape I'll talk about here, and there are others, but these are the basic ones, is called a uniform distribution. So in this case, the example is a random lottery number. So the numbers across the horizontal axis are lottery numbers, in this case from 0 to 100. And the frequency bars are not all exactly the same height. We see some taller ones and some shorter ones, but the heights are roughly the same across the whole distribution. So there's not really one range of lottery numbers that are more likely or more common than another. This uniform distribution is what we would expect from uniformly distributed data, meaning kind of any lottery number has an equal chance of being chosen. An ideal uniform distribution would have frequency exactly equal all the way across, but with real data, that's not typically going to happen. You're going to have some random noise, even if the population data was actually completely uniform. That's it for this video. Thank you for watching.